Okay, sorry. Ladies and gentlemen, welcome to another wonderful episode of the New York City Category Theory Seminar. Today we have Gabriel Goren-Roig, you'll say it better, talking about arboreal adjunctions from shapes. Take it away.
Okay, thank you, and also thank you, everyone. I will assume that you can hear me and see everything. For some reason that I can't solve now, I can't see even your faces right now. So I just see my own slides. So
Uh,
hopefully, if there's any problem, you will tell me. So
and
thank
I'll tell
yeah.
you, and I'll tell you what's on the chat also. So don't worry about that.
Okay, great. Thank you. So, thanks also for the invitation to this very cool seminar. So I will be talking about joint work with Tomáš Jakl and Luca Reggio on this topic of arboreal adjunctions and how to obtain them from shapes. So I will spend quite some time on an introduction. I'll actually try to time myself. My goal is to convey the main ideas through this introduction. So if that's all that you get from this talk or all that I can explain well, then I am satisfied with that. And the rest will be a deepening of those ideas, getting into some more technical details. So we will start by
By the way, that's
thinking about
perfect because I never heard of an arboreal adjunction before reading your abstract.
yes.
So
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 we'll
stick to that
perfect.
and perfect.
So let's start with graphs with edges. So directly graphs with edges labeled or rather colored red or green to have something concrete to look at. And we'll also fix a base point for these graphs. So we will think of it as a labeled transition system where the vertices are states and these red or green arrows are behaviors that might lead from one state to another, or more generally, sequences of these movements will be called behaviors. So a question is, what are all the possible behaviors of the system? Of course, starting from our chosen base point. In this case, is this vertex labeled 1. So a way to answer this is by recording all possible paths starting from this base point and also recording which transitions are crossed at each time step, so to speak. So we're starting at 1, we can first traverse the green arrow and then the red arrow to 3, or first traverse the red arrow, which is actually a different thing because it's a different behavior, even though it leads to the same state, and then go to 4, and then we might loop any finite number of times using the arrow from 4 to 4. Okay? So these would be the behaviors. Now, the interesting thing is that we can assemble all of these behaviors into a tree. So it will be the tree R of this pointed graph. And so the vertices of this tree are the sequences that I was describing. And then we can place edges between these vertices, which will correspond to extending extending one sequence by one new element, and then we can even color these edges by the color of the last edge in the corresponding behavior. So we are actually obtaining an object of the same category that we started with. And what's interesting about this construction is that the result is behaviorally equivalent. So any moves you can do in the original graph, starting from your chosen base point, can be mimicked or duplicated in this new graph, and vice versa. So there's a technical way of saying this, and it's called bisimilarity. So we
Gabriel, broad. You take a graph and you're making another graph. You're making a tree out of the graph.
Yes. So in particular, it's a tree, but it's colored in the same way as the original graph.
Okay.
Yeah. So it's what I'm trying to say here is just notice that the result is can be seen as an object in the same category of directed graphs label with colored edges, basically. So, and the reason why I'm emphasizing that is that because this is an endofunctor, and it is actually the functor part of a comonad. And this is a very classical construction. It's called the unraveling or the tree unraveling, or there are some other names for it, but this is the one that I'm using. And by the way, I apologize for the non-professional quality of the images, but I hope that they convey the meaning well enough. So there is also a logical side to this picture. And in this context, the logical counterpart would be modal logic or basic modal logic, which actually allows us to reason about these behavioral properties by expressing them as formulas in a certain syntax. So for instance, the fact that we can traverse a green arrow followed by a red arrow can be expressed as a formula phi, like this one, where these things with angle brackets, they're called modalities, or they would correspond to like the diamond modality in modal logic with just one modality. And this top symbol at the right just means true. So we're not saying anything else except like the only interesting part of the formula is this modalities. Yes? Was there a question?
No, 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 we're okay. Sorry, go.
So basically, this formula is saying from wherever I am, there exists some successor that is accessible through a green arrow, such that, then the formula continues, there exists a successor following some red arrow, such that true. So that's the intuitive meaning of this formula. And the fact that it's true at the vertex 1 means that there's precisely a path like that one, right? Then this bisimilarity thing that I mentioned is relevant because it actually ends up coinciding with this other notion, which is logical, which is to say that these two graphs satisfy exactly the same formulas of modal logic. There is a syntactic relation, or, well, I mean, it is semantic, but it uses the syntax. And then there's this purely semantic or behavioral notion, which is bisimilarity, which I haven't defined, but trust me that it doesn't use a syntax. This talk is in the broader context of this program called comonadic semantics, right? And this program could be seen as the observation that this story generalizes to many other logics, not just modal logic. So I will try to explain what this situation is, or what I'm thinking about as this situation. So we start with some logical language, L, which induces an equivalence class on the structures that it talks about, right? So in case of graphs, well, two graphs satisfying exactly the same formulas of this language. Then it turns out that this often coincides with some behavioral or semantic relation, which we will generically call a bisimilarity relation. But maybe that's a well-known, a more used terminology in the case of modal logic, but it can also refer to an analogous thing in first-order logic and so on. And then the observation, the categorical observation would be these bisimilarity relations can often be captured by a comonad on acting on this category of objects that the logic is predicating on. So these are called the extensional objects. So that's the category E for extensional. And these objects would be basically graphs in the example that we've been looking at. And even more generally, we don't really always need a comonad. We just need a certain adjunction. So we will have our category, our extensional category E, in relation to another category A through an adjunction. And if this category A is an arboreal category, which I will define in a bit, then I can actually express some bisimilarity relation. How? Well, every arboreal category has a bisimilarity relation between its objects, which is well behaved in different ways. And using the adjunction, we can transfer this relation to speak about objects of the extensional category. So just terminology, this is an arboreal adjunction. It's an adjunction where the domain of the left adjoint is an arboreal category. I still need to say what an arboreal category is, but this is the object that we're studying. And so, first of all, I want to tell you how we will obtain these adjunctions, and we will do it by generalizing this unraveling construction that I presented just now. So, to generalize it, we will look at it from a different angle. So, we had looked at this tree where the nodes were sequences of nodes and some labels or some symbols to represent whether it was red or green that was traversed. Now, I want you to think of this as sequences, but sequences of homomorphisms into our object. So these are homomorphisms from a certain class of shapes that we will call S. And in this particular case, this class has just two objects, two graphs. The graph with two vertices and one red edge between them, and the graph with two vertices and one green arrow between them, as we see on the left. And notice that these shapes have a source and a target. Right? There's a source vertex and a target vertex. And we are looking at maps from these shapes into the graph G that we chose kind of randomly as an example. So, for example, we had this sequence on the left, which read move to node number 2 through the red arrow, then through the green arrow to 4, and then traverse once the loop at 4. And I want you to reinterpret this as a chain of 3 homomorphisms, where the first one goes from the red arrow to, and its image is this first edge. The second homomorphism has its domain, the green arrow, and maps it to this arrow here. And of course, the same for the third homomorphism, mapping again from the red arrow to this loop. And notice that this is a kind of like a probing thing, but it's sequential in the sense that the first probe has to map its own source to the base point of the graph. And then each successive probe or homomorphism has to make the consecutive endpoints match. And in this sense, it is also a kind of path or walk inside our graph. And if you think of it in this way, then you can ask yourself, well, what if I want to probe with other things that are not just edges, right? So for instance, we could consider shapes that have more than 2 vertices or different kinds of configurations. So here's an example with 3 shapes on the left, and that we might want to use to probe this other graph G. Now there's no colors anymore to make it simpler. So on the logical side, this is interesting because it would correspond to having other logical modalities or operators which are indexed by these shapes. And this would express the presence of these shapes in the graph that you're looking at. So the expressive power of these logics would be different. And you could do, again, a similar kind of tree construction, where every node is actually a sequence of chained homomorphisms. But it's nicer to draw it this way, where instead of putting each sequence at each node of the tree, I just label it with the shape of the last element from that sequence. So what you end up having is this thing, which is a tree, where every node, except for the root node, is labeled by these shapes. And that is what we will call a shape-labeled tree or an S tree. Okay, so of course, in this case, you start mapping in different ways, and in what ways you can keep on mapping from the endpoint of the last map and so on. You get an infinite tree, but that's not a problem. Okay, that looks interesting. But we want to reproduce the whole thing, and this is not a comonad in the obvious sense that we started from a graph and then we produced this tree labeled with graphs. So to obtain an object in the original category that we started with, there's an extra step that has to be taken, which is to glue together all the shapes. And of course, there is a natural notion of how to glue them, which is by identifying those source and targets, consecutive source and targets of the shapes. So you do end up getting something of the same kind as you started with. And this will define a realization functor, or we will call it realization, mapping any shape-labeled tree to a pointed graph, which is pointed in the same sense that the tree had a distinguished root, which will end up being the distinguished point of the graph.
Gabriel, can you say again how you made this tree?
Yes, so I might have, yeah. So let's go.
Is it a coend?
No, I mean the tree is just defined by hand. So I will describe the definition more formally in just a second. But basically, so originally the tree is actually comprised of these sequences of maps. Each node is a sequence, but I am representing it by looking at the domain of the last element of the sequence. So where I place each of these shapes here, these are the domains of the last element of the sequence. That's how I am drawing them. I don't know if that answers the question.
So you have a child node if it's attached to the end of the previous node.
Um, yeah, exactly.
Right?
That's yeah.
Okay.
So I mean, there's yeah, because once you have the tree, of course you forgot, these are just nodes. They're how you label them. The fact that you label them, you construct it as sequences is useful, but once you've done that, you treat it up to isomorphism. So the nature of the node itself doesn't really matter. What matters what you're labeling it with, which is the shape.
And you're always considering directed graphs.
Yes, this is always
Okay.
directed.
Just to be sure I understand correctly, when you make a graph from the tree, you will have a single graph, not multiple graphs, one for each path.
Yes, precisely. So once you take this whole tree with a bunch of graphs and you glue them together, you get a single graph out of it.
And the main big point corresponds to the empty sequence of homomorphisms.
Exactly. The empty sequence of homomorphisms is this dot on the left of everything, and that is going to be the root of the tree, and then it's also going to map into the base point of the new graph. So right, I want to say a few more words before jumping into the details of why or what's new about this approach in the context of what we're trying to do in comonadic semantics. So by now there's something that we could call the usual script, which is great, really, and the fact that it's worked is amazing. So the script goes as follows. You start with some logical language. These tend to be fragments of first-order logic, or sometimes maybe some second-order logic thing. But it's the kind of logics that people are interested in computer science, especially with respect to complexity and things like that. That's kind of the focus. The kind of logic that this framework is trying to target. And then, well, I didn't really talk a lot about games, but this bisimilarity relation is actually, it's nice to represent it as a game played between the objects. So here I'm saying, well, from the logic, there's a well-known game in the literature. This is the bisimilarity relation that I mentioned before. And then we figure out if we can construct a comonad out of that game. And then this comonad turns out to have an arboreal category of coalgebras. It's Eilenberg-Moore category. It's the category of coalgebras of the comonad. And when we look at the Eilenberg-Moore adjunction corresponding to that comonad, that is the arboreal adjunction that we obtained. Right? That's how you get an arboreal adjunction. Now, the new thing, or the problem, it's not necessarily a problem, but the weak spot of this is that it's not very systematic, right? So we would like to explore this landscape of adjunctions in a way that at least gives us some machinery to obtain new examples, basically, without having to handcraft them. So that is what we're trying to do here. So we will start with a class of shapes, which has to satisfy some assumptions. And then from that class of shapes, we obtain an arboreal adjunction of the S trees over the pointed objects, whatever those are. So that is the what's exciting about this, right? Oh, and of course, this also gets to the logical side, right? Like there is, as I said before, in any arboreal category, there is a notion of bisimilarity, there is an associated game. And there is a logical syntax that should go with it, although we haven't really worked out that part formally yet. So yeah, I haven't said this before, but this is very recent results. This is very much work in progress. So there's a lot of things that are still not figured out not because they're hard, just because we're still working on it. So this is the introduction. This is the statements that I will try to explain in the rest of the talk. So there's two results. The first one is if we start with the category S. So now notice that S is not a class of graphs, or it's not a class of anything really, it's just a category. And we will require that the morphisms are epimorphisms. Then there's an associated category of shape-labeled trees, which is arboreal. Okay, that's the first result. It doesn't really talk about any extensional objects. It's just a category where the objects are, we choose to call them shapes, that's all. And there is a caveat that arboreal categories actually require a factorization system. So I have to explain which factorization system I'm going to impose on this category in order for this to make sense. So that's the first part. And the second part is, well...
Did you say what S tree is as a category?
No. No, the things in blue here are things that I have mentioned, but I haven't defined formally yet. And the things in orange are things that I guess I have already mentioned arboreal, the notion of arboreal, but these are things that I also have to define in order for these statements to be completely meaningful to you. Okay.
Gotcha.
So yeah, so I'm going to get into the definitions just now. Right, so the second result, what it says now, we will consider a co-complete ambient or extensional category of objects, which you should be thinking of as directed graphs, although really there is a level of generality here that is still to be completely determined. But of course, it's not just graphs. And then we will identify this category of shapes with bi-pointed objects, which I'm also going to define, but you have the intuition by now, hopefully, that is objects with some source and target things. And once we identify our shapes with this choice of bi-pointed objects, then we can define a realization functor that does something like what I showed you before. And then there's the facts. Fact number one, I will have to put some conditions on this category S. You might have noticed I started talking about classes of shapes, and now they're not classes anymore. They can have morphisms between them. That makes things more complicated, and it actually requires us to introduce more complicated assumptions. So here in orange, we have a complicated assumption, which is that this functor that identifies every shape with an object from E has to admit something called a right multi-adjoint, which is a weakening of the notion of a right adjoint, which I will try to explain in the time I have. And if that is the case, then we can obtain a right adjoint R, which does something like what I showed you before, where you get a tree labeled by the shapes that you can map into the original object. And then there's the question, well, we do get a comonad, but do we know that comonad really well? Do we know the coalgebras of that comonad? And it turns out that at least if we add some other assumptions, such as, for example, if we're working with directed graphs, then this functor is not just a left adjoint, it's comonadic, which means that the coalgebras are precisely the S trees. So we already know them, and we know how they work. And and that's also important for the framework. So these are the results. I will also assume stuff categories to be well powered is a size assumption that I don't want to get in, but it has to be there. And yeah, that's, I mean, if you listened until this point, then you mostly know what I'm talking about. The rest is getting more formal and, you know, of course, saying what things really mean. Is there any question right now? Okay, I'll assume there are no questions and you still hear me?
Yeah, we hear you. No questions. So far, so good.
Great,
So you're about
great,
to
thank you.
answer one of our questions.
You're about to answer what an S tree is. Go.
Okay. Probably, yes. So let's go to the actual meat of the thing. So we fix a category of shapes, as I was saying. This is just a category. And we will define an S tree as, first of all, a tree. So for us, a tree means it's rooted. So it's a rooted tree. It doesn't have to be finite, but there is a finite path from every point, from every node to the root, or rather from the root to the node. And then I will also mention a lot of tree morphisms. The tree morphisms have to respect the root, and they have to respect, you know, the successor relation in these trees, or the successor or child relation, however you want to call it. And then there's a labeling function, which is this lowercase t. And it's basically a function that assigns some object of the category S to each non-root node of T, right? So here I need you to remember that it made sense, or hopefully it made sense before, that when I showed you that example, it made sense that the root didn't have any shape assigned to it, because it's just telling you how everything else is going to be glued together. Intuitively speaking, there's no gluing here. So those are the objects of the category. And now we have the morphisms, which will consist, first of all, of a tree morphism between the underlying trees. So we have shape label trees T and Q. We have the underlying trees. And then what we are specifying is a morphism between them. But now we have to say something else, because these trees are labeled with shapes. And shapes form a category that has morphisms in it. So we actually want to include, as part of the data of the morphism, a family of shape transformations or morphisms between shapes that I call gamma, indexed by all the non-roots of the tree X. And what it does, well, basically it's just a choice of a morphism from the category S for each X, which goes from the shape that is contained in node X to the shape contained in node f of X. Here it would be nice to have a picture for that. I'm sorry, I don't have it. I do have a diagrammatic representation of this, which might make you think this gamma is kind of like a natural transformation, except it's much simpler than that, because there are no naturality squares. But you could think of this as a kind of trivial natural transformation. So these are the morphisms. It's a morphism of trees, and then at each node you have an extra morphism of the shapes. And then there's a special kind of tree, which is the paths. So the S paths will be the S trees whose underlying tree is just a chain, so a finite linear order. And that is nice because we can, for instance, write them as just a sequence of shapes, because that's the tree is just basically a sequence. We write S tree for this category, and S path will refer to the full subcategory of this S paths. So this is the definition. Hopefully it makes sense. And the thing we want to show is that this is arboreal. So the footnote here says there's actually two definitions of arboreal categories in the literature right now. So I will present the second one, the newer one, even though in this case it turns out that this category satisfies the two definitions. But the new definition actually solves some problems that were noticed in the literature. So it's the one that we should be using in general. So first of all, as I said before, in order to express these axioms, we need a factorization system, right? So I will not get into the details of that. I will just quickly recall a factorization system. QM is actually, Q and M are classes of morphisms in our category A. And as what it means for this to be a factorization system is that any morphism can be factored as a morphism from Q followed by a morphism from M. And we'll call the morphisms from Q quotients and the morphisms from M embeddings. Right? So that's the names, the intuition. And well, we require a couple of things about this factorization system. There's a stability condition that I won't get into, I won't mention it. And then there is a properness condition that I will mention a little bit, which basically says that all the quotients should be epimorphisms and all the embeddings should be monomorphisms. So you should be thinking of Q and M, or in general, as some special kind of epimorphisms and some special kind of monomorphisms. And so the first thing we use this for is to define path objects. So what is a path object? It's an object such that its poset of M subobjects is a finite total order. So if you have an object in your abstract category and you ask yourself, what's its shape? Like, what does it look like? Well, you can look at the subobject poset. And actually not just the normal subobjects, which are defined with respect to monomorphisms, but actually M subobjects defined with respect to this special kind of monomorphisms. And you require that to be a finite total order. So that's a path object. And then there's a special kind of diagram that we have to look at in this category, which are called tree diagrams of paths. These are diagrams in our category which are indexed by something that is a tree, so a category that is actually a poset and it's tree ordered. So trees start to appear in different layers here. So this is a tree-shaped diagram in our category in our arboreal category of objects that should somehow be trees in some sense. So that might get confusing, but it's just a diagram in our category. And we require the index category to be tree shapes, we require the objects to be paths, and we require the morphisms in the diagram to be embeddings. So that's a tree diagram of paths. And then, well, that's the definitions we need. We have the factorization system in place, and now we can state the arboreal axioms, right? The first axiom is that there's a connectedness or connectivity condition for paths. So first of all, every tree diagram of paths has a co-limit. We don't require the category to be co-complete or something, but sometimes it is the case. We just require these tree diagrams of paths to have co-limits. And then every time we map into one of these co-limits from a path, this map should factor in a special way through the co-limit. It should factor through the co-limit in a minimal way. The second axiom for arboreal categories is that this full subcategory of paths is actually dense. So I won't give the formal definition in full detail, but what this means is that every object in this category is a canonical co-limit of paths. So maybe to explain a little bit more for the people who haven't seen this definition before, what I mean is, given any object, there is a canonical diagram comprised of all the maps from all paths into this object. Well, this is actually a cone over a certain canonical diagram. And then the requirement is that this cone is universal. So the object is actually a co-limit of its own universal canonical diagram.
Can you explain number one more?
So I think, in order to explain it in a lot more detail, I would like some example and some picture that I don't have right now. But what I can tell you is this. So it has to do with point number 2, actually. If you look at all the paths into an object, that gives you a cone. but you can actually factor the entire cone using the factorization system. And then you get a diagram, or rather a cone, where all the legs are embeddings, right? So in a sense, I expressed it in terms of density because that's a well-known, like a general categorical concept. But here, what's going on might be explained more specifically as every object being a canonical colimit of a certain diagram where the objects are paths, the morphisms are embeddings, and it is actually tree-shaped. So the diagrams that appear in point number 2, they're also tree diagrams of paths. So we really just care about tree diagrams of paths. And the condition number 1, it's saying that there should be something well-behaved about paths, not just with respect to these canonical tree diagrams of paths, but even with respect to non-canonical tree diagrams of paths. Like the tree diagrams of paths are more general than the canonical diagrams in point number 2. So that probably doesn't answer your question, but it does give you a connection between the 2 points.
Yeah, it's pretty good.
Well, what is a minimal leg?
A minimal leg. So this is column D. The diagram is indexed by a category I, but the category I is required to be actually a tree. So when I say a minimal leg, it means that it's minimal with respect to the ordering in this tree. So there's at least I, lowercase I in I, such that the morphism factors through it.
Thank you.
Sure. Thanks for asking. So these are the 2. I mean, I think there's already enough stuff to think about with these 2 axioms. There's a third one, which has to do with quotients, but I don't even want to read it because I'm not going to talk about it anymore in this talk. But it's there, and it serves a purpose too. I'm just not getting into that. So yeah, a question or not? Okay. So that's the abstract definition. Now I have to give you a concrete factorization system that works for S trees, and then I'll try to give you some intuition for the rest. So we're going to take one morphism between 2 S trees, which has the tree part and the shape part. We're going to say it's surjective if the tree part is surjective, and we're going to say that it is iso-injective if the tree part is injective and the shape part is just made of isomorphisms. So that's what iso-injective means. And then we're going to say that the quotients are the surjective and the embeddings are the iso-injective morphisms. And this works. So this gives a stable orthogonal factorization system. The path objects, you have to ask what those are, and they are what they should be. They are the S paths, so the objects where the S trees where the underlying tree is linear. And then there is something else. I haven't said, so until now, the category S was kind of arbitrary, but now if we further require that the morphisms are all epimorphisms, then we get properness. And this will make sense after I give you the idea of how you obtain these factorizations, which is, it really looks like cheating. So consider some morphism F gamma from T to Q. We know there's an underlying morphism of trees, and we have a factorization system on trees. In fact, this is something that I haven't said, but the category of trees is arboreal. It should be, right? Because otherwise the terminology is all wrong. So basically, what we're doing here is reducing things to showing that we can lift things in the category of trees to the analogous things in the category of S trees. This is what we're doing here. We look at a factorization in the category of trees, and it's just factoring the function through the image of the function, basically. And then we have to extend this to some factorization on the shape transformations, which, remember, is a collection gamma that is indexed. Well, here it should say gamma sub x, right? It's a collection indexed by this variable x that ranges over the nodes of the domain. But now we just do a trivial factorization because the shape in the intermediate object is the same shape as the one in the codomain, because it's just well, I guess that's also something that I have to say. So the intermediate object is a tree, but I label it exactly as with the same labels as the codomain, so that it really looks like an image. And then I can just put the identity on the second part. And because the second factor is an identity, the first one I can just repeat. I can just put the original morphism I had. So that's why I say it's cheating, right? Like it's at the level of shapes, I'm just factoring a morphism as itself followed by the identity. And this works, except for the fact that unless I know for some reason that all these gamma x are epimorphisms, the quotients are not epis, right? So it does give you a factorization system in which the embeddings are always monomorphisms that can be checked easily in this category, but not the quotients. The quotients can be anything. Well, I mean, the quotients are surjective on the tree part, but on the shapes they can be anything. So they might give you something that is not an epimorphism. Right. That's why I wanted to mention something about properness. So this factorization system works, and we have the theorem. If all the morphisms are epimorphisms, which we require for this factorization system to be proper, then the category is arboreal, so it satisfies all the other axioms. And I'm not going to give even a sketch of proof, just like I'm going to repeat what I said before. The proofs of these things like tree connectedness and density, they can be reduced to the analogous facts in the category of trees. One way of saying this is that there's a forgetful functor from S trees to just trees that just, of course, forgets their shapes. And this functor creates the co-limits of tree diagrams of paths. And it does so because tree diagrams of paths, iso-injective maps, they're almost the same as just the underlying tree morphism, because everything else is an isomorphism. So even though it does technically have extra structure, it's isomorphisms. So yeah, I guess I can't say anything more concrete than that right now. But these arguments work, and they work regardless of whether we put this condition on the morphisms of the shapes, that they are epimorphisms. It's just that by definition, an arboreal category requires the quotients to be epis. Now, it is an open question how much of the theory is lost and how much of the theory is retained if we drop the requirement that quotients are epis. So there might still be some situations in which we could consider S trees without this assumption. But it's something to be seen in the future. So that's it. That's for the first statement. So we have an arboreal category. That's one half of what I wanted to show you, right? The other half is, well, the more interesting part where you say, well, how does this arboreal category relate to potentially to some categories of interest? So if there's any question, please interrupt me. Let's go. So now we are starting from an ambient category, E, and we require it to be co-complete. And we'll also fix an object, star, that will play the role of the point. So part of this can be said and done in this level of generality, which is a bit higher. Of course, then at some point I will go back to graphs, and then the star is just the singleton graph with no edges, as one would expect. So some terminology. We have the full subcategory of the monomorphisms from the point into extensional objects. So this is what I mean when I say a pointed object. It's a mono from the star to an object. And then we have the bipointed objects, which, as could be expected, are cospans of monomorphisms. And we require that they are not equal to each other, even though this condition can probably be dropped, but it's there just to be safe.
And you don't want this to be the terminal object, the point?
No, no, that's not necessary. The right level of generality here is still to be seen. Like this, maybe should be said more generally or less generally, and like this is just the level of generality that we have it right now. But you don't need it to be terminal.
Okay.
And so now our category of shapes is a possibly non-full subcategory of the bipointed objects in E. And this is what's going to connect the S trees with the extensional category. This is intuitively similar to how we can realize pre-sheaves. So that's also maybe part of why we're calling this a realization functor. So if you have pre-sheaves over C and then a functor from C to D, that lets you see the pre-sheaves as some kind of gluing specification, and then you can glue that and according to F and so on. So this is intuitively analogous and maybe even formally analogous in some sense, but that's not clear yet. And so what should this diagram be that we're taking the co-limit of? It's easier to look at in the case of a path, although the idea is always the same. So what we want is to take all these shapes and glue them along the endpoints, right? So what we can do is on the second row of this diagram, we have first the point, which represents the root of our path, the empty sequence. And then we have at each node, we just have the corresponding shape. And to glue them along endpoints means that we consider spans from the point that are precisely given by the start point and the end point, or source and target of every shape, because they are bipointed. So then we just take the co-limit of this. So to say this more formally, what we're doing is the shape of the index category of this diagram is the barycentric subdivision of the tree. In this case, the tree is just a path. So what that means is that all the objects are both vertices and edges, and for every edge we get a span, right? Like two morphisms out of it. So that gives us the shape of the diagram, and then we have to define a functor out of that shape, and that gives us this diagram D of an S tree T, which does what is seen here on the picture. So each vertex is sent to the shape at that vertex, and we have to extend that to saying that we send the root to the singleton, sorry, to the point object, which was not part of the definition before. Each edge object is sent to the point too, and then the spans are populated, let's say, with the endpoint maps of the shapes. And that's all. That's our diagram. So now we just have to take the co-limit. So that does define a functor. The functor acts on an S tree by taking the co-limit of this diagram that we just described, and then you also have to give it a point, or like a base point, and that base point is given by the root leg. So if we imagine this diagram here as sitting over the co-limit with all the co-limit cone, then the leg from this one here to the co-limit will give the base point. Hopefully that made sense. And then on morphism, it's just basically a co-limit, right? So it just works as it's induced by the universal property of co-limits, but we can be a bit more. I guess we don't need to be more specific right now with this.
What is E? E star?
So E is our category of extensional objects, and E star is the category of pointed objects, which means objects with a monomorphism from the point.
And to define S tree, did we fix E?
So we
tree.
did, yes. So what we did was sorry, here the assumption is that now this category that abstract before, now it's actually pointed objects.
Okay.
So now it's not abstract anymore. It's a category of, it's a choice of bi-pointed objects in E.
I see.
So, oops, sorry. So, and here's just the remark, especially for you, Emilio, that this first part of constructing this diagram, it's landing in an intermediate category, which is a category of diagrams. More specifically, it can be called the category of tree-shaped, E-valued structure decompositions, in the sense of Bumpus, Kočiš, Master, Minikelo. And I find that really interesting, but that is definitely a connection to be studied in the future, if there is something to say about it. But we really are, in a sense, S trees are a category of, in this sense, a category of structure decompositions with certain morphisms between them. Now we're almost done with the general, we would be almost done, let's say, if we restrict to discrete choices of shapes. Because if we do that, then we can go ahead and define this R functor just like I showed you in the introduction. So to make it more formal, say that a chain into an object X, pointed object, or more fully, a chain of morphisms into X is a sequence of morphisms where the domains are shapes, such that the source of the first shape is mapped to the base point in this sense, right? Like now we don't really have points at this level of generality, so I'm just describing that with precomposition by the map from the point. And then in the same sense, the consecutive endpoints match. So it's the same intuitive idea of a chain that we had before. And the reason why I say we would be almost done is that this functor R would just be, well, from a given pointed object, it just constructs a tree of all chains into it. And every chain is labeled with the shape that is a domain of the last morphism, just like I showed you in the introduction. Now, this doesn't work if the category S is non-discrete. I will try to give an explanation of why we care about the non-discrete case. I mean, from the categorical perspective, it is quite natural to wonder about it, but it's also interesting from the logical side. So now, if S is not discrete, I will, in order to find a way of describing this right adjoint, I will have to introduce an assumption, which is this thing involving right multi-adjoints. So here I'll try to quickly explain what that is. I know I'm like quite bad in terms of time, but there's a lot of stuff that I can skip, so I'm not that worried. But
you're doing good on time. It's fine.
Okay. Thanks. So what is a right multi-adjoint? So take a functor U from A to B. What we say that it has a right multi-adjoint if for every object of the codomain there is a universal family into it, which means a family of morphisms from U of some A sub A to B, that are universal in the sense that for any morphism G from UA to B, there exists a unique element of this family and a unique intermediate morphism zeta, such that our G factors through factors like this. So U of zeta followed by the universal map. So this is kind of a complex maybe at first sight, but the only thing that like what I want to highlight is that this is a weakening of the notion of a right adjoint, and you should be thinking about this universal family for some choice of B as playing the role of the co-unit of an adjunction. Usually the co-unit is just one morphism, right? For given B, there's a co-unit map for B. Here, there's more than one. And this entire family is sharing collectively the universal property of the co-unit. And that is exactly what is said here with this in this diagram.
Now, I remember you introduced, I'm sorry. I was going to say, I remember you introduced this earlier as a weaker condition that was needed that would give you an actual adjoint in your theorem.
Yes. So here, yes, I'll get to that right second. So it's a right multi-adjoint that I need somewhere to get a right adjoint somewhere else. It's not between the same pair of categories. But yes, well, this is this is weaker than the notion of an adjunction. That's what I was trying to say. It was introduced in the 80s, as far as I understand, by degli, studying spectra of algebraic objects, like different kinds of rings and different kinds of spectra. And it is interesting that this is appearing here as a dual, right? Like, because he studied left multi-adjuncts. Here, the right multi-adjuncts are appearing, and it makes sense because these extensional categories are not very algebraic. They look more like maybe geometric or co-algebraic in some sense. And then also there's another notion, weaker notion, which is maybe more well-known, which is parametric adjoints. So I just wanted to mention that these two notions coincide. Multi-adjoint and parametric adjoint do coincide under some conditions, but we're not interested in those conditions specifically, like right now. They might or might not hold for our cases of interest. So this is the definition. And now the assumption is that when we look at shapes as objects, like forget about the points, forget about the endpoints. When we look at a shape as an object of E, then that functor admits a right multi-adjoint. And we fix a choice for these universal families because we're going to use it to define the functor. And then there is this condition in gray that turns out to be actually necessary for it to be a functor, but it's just a technical thing. So because we're not writing this forgetful functor explicitly, I just want to show you how the triangle looks in this case. So we have some morphism alpha from a shape to our object X. We're going to write alpha bar for the unique universal representative that it factors through. And then we also get a zeta sub alpha like this. That is the factoring map between alpha and this alpha bar. Alpha bar will be called the saturation of alpha. And we say that a morphism is saturated if it's equal to its own saturation. So the saturated morphisms will turn out to be very important. And we'll say a chain is saturated if each morphism in the chain is saturated. So here's an example that I will try to use later on too, if I have time. So consider now this category of shapes where we have the shape D, which would be called like a diamond graph, and the shape C, which is the collapsed diamond. I'm calling it like that because I'm also including the quotient map that identifies the two intermediate vertices into this one. And that's it. And then, of course, the identities. That's the category. Now, we look at morphisms into a triangle, a directed triangle like this, where, well, of course, there is a base point, that is this leftmost vertex, and these things do have a base point and an endpoint too, depicted left and right. And then the example is, we can look at this map. There's a unique map from the diamond shape, the diamond graph to this triangle. There's also a unique map from the collapsed diamond to the triangle. And of course, this one factors through the other. What I mean is the only morphism that you can find from the diamond to the triangle actually sends everything to this length 2 path on the top of the triangle, right? So because this morphism factors through the other shape, then it's not saturated. In fact, if I take this morphism alpha on top and I saturate it, I end up getting the morphism below. That's what the operation of saturation is doing. And so now we can give the definition of the functor. into S trees. The main thing here is it's like before. We look at all the nodes of this tree will be the chains into X, but now we require that they are saturated. If we have a chain of morphisms that are not saturated, we just don't include it in the tree.
So you're assuming that some multi-right adjoint exists in order to define this? And then say what does saturated mean again?
So saturated means that it's part. So basically, it means that it is part of one of the universal families. So
but you're defining the universal family, right? You're saying given a universal family, it's saturated if it's in that thing.
Yes, but it's unique up to some kind of isomorphism in the same way that a normal right adjoint is unique.
Okay.
So what I'm saying is kind of like fixing the right adjoint. I'm saying fix the right multi-adjoint, because if you don't fix it, this functor is actually not defined. So yes, so the point is you might have to choose between isomorphic objects when you're constructing this right multi-adjoint. You have a non-canonical choice there to make between isomorphic more arrows or something like that. Does that make sense?
Can you go back to the last slide? How did that? So okay, so you have the S, directed triangles, factors through that. Why is it not?
So let me explain it a bit. Let me explain it a bit more. So in this case, there's a unique map from D to X and a unique map from C to X. Because they are unique, they are universal. They are in the universal families. Because remember that for a universal family, I have to choose for every, so B here will be X, it's fixed. And then well, I guess it's not so easy to see from this definition. There's another definition that makes it simpler to see. But the point is because there is just one map in this hom and one map in this hom, that means that they are universal.
Okay.
Wait, no, I'm saying it wrong. That is not true. What I'm trying to say is that's the reason why this map is universal. But the one in the top is not, because it can be factored through the other. So, sorry, I just made a mess. The point is that you can see that this map, the lower map, is universal. And then because this map factors to the universal one and they're not equal, this one is not saturated. It's not universal.
I see. Okay.
Are synonyms. I'm just saturated is more intuitive for me than saying universal once you start using it in this context.
Gotcha. Okay.
Okay, hopefully it makes more sense now. So what I'm going to do is I'm going to skip, I think, the definition of how this functor acts on morphisms. It is actually more involved because, well, I'll just say this. So what would be the obvious definition? You have to map a sequence of morphisms into another sequence, and you have an F. So you can just post-compose every morphism in the sequence, and you get another sequence which with a right domain and codomain. The problem is that there's no reason at all why this would be saturated morphisms after you do that. So you then have to saturate them as part of the definition, and that's what these bars are doing here. And then you also have to say how this acts. You need to define the shape transformations at each node of the trees, and you do that using these factorizations. So this does give you a right adjoint to the realization functor, and I wasn't planning ever to give you like the checking of this, but I did want to describe the unit and co-unit. I will do it kind of like, I'm not sure this is a good intuitive thing, but I tried to make it intuitive. So the co-unit, so it's mapping out of a co-limit. So you define it by universal property, and since the co-limit legs are have as domains these shapes, then you can just use the last element of the sequence as your cone, so to speak. So this is the picture I have in mind. Hopefully it makes some sense to you. So this thing on the top would be M of R of X. What you do is you look at the chains into X, so the chains of all maps into X, and then you realize that by gluing the shapes together. And then basically what you're saying is, well, if I restrict, in some sense, my epsilon, if I restrict it to this part here of the object that is here because of a sequence of gluings that I did sequentially, then epsilon here is just alpha. Hopefully that makes some sense. And then the unit, the other way around. So here we start with a tree. We realize the tree, and then we look at saturated sequences into that tree. So imagine your tree has a branch with shapes S1 to SL. It doesn't have to be the entire tree, but just a branch of the tree. And so when you realize this tree, you will get something that looks like this, which would be like a sequence of shapes glued at the endpoints. And because you, because this was glued from maps into, sorry, not from maps into it. So what I want to say now is that you do have, because the tree was labeled with these shapes, you have maps from the shapes to these cells, so to speak. And again, the thing is, these maps might not be saturated, so you have to factor them through the corresponding universal map, which is the I bar, and that gives you a branch in Rm of t. And once you have identified this branch, then you can just define eta to map one branch to the other. So in a sense, every branch in your original tree is reflected somewhere in some branch of the new tree obtained.
So eta saturated things piece.
Yes. So eta. So if you want to look at it as just one formula, where is it? Oh, sorry, here. Yeah. So so you have to look, given an x, because it's a tree, it's a node in a tree. You have a unique path from the roots, and then you have the embeddings into the gluing corresponding to all these nodes, to all these shapes in these nodes. So that would be the sequence I sub x1 and so on without the bar. But then by definition, you need to give a saturated chain. So you saturate it.
And if S is discrete, then the saturation just doesn't do anything.
Exactly. If S is discrete, then all these bars disappear. So that's, yeah, hopefully gives some intuition of how this adjunction works. And then the last technical thing that I want to mention, even though again I'm not giving full proofs, is the comonadicity part. So let's just call D the comonad arising from this adjunction. From now on, I will go super concrete and say that the extensional category is just the category of directed graphs, and the star object is the singleton graph with no edges. So I'm brutally changing levels of abstraction. This is, most of this is to make sure that we have underlying sets, and these sets get glued along single points. So this should be true. What I'm going to say now should be true in quite some more generality, but because it's work in progress, it's recent, and just to be safe, I'm stating it in terms of directed graphs. And so the theorem is that if we choose our extensional category to be graphs, then this functor is comonadic. And in particular, S trees are the coalgebras. So here I omitted the assumption. So I'll remind you what the assumptions are. So I assumed that the shapes S form a subcategory of bipointed objects in graph, so bipointed graphs. I did assume that that all the morphisms in S are epimorphisms. I'm assuming that. And I'm also assuming that there is this right multi-adjoint that gives me this saturation operation. Like I need to be able to saturate the morphisms. And so just, I mean, this is almost nothing I'm going to say, but so the idea I want to give you is, well, how you prove this, you look at the comparison functor into the Eilenberg-Moore adjunction from this adjunction that you started with, and you want to give a quasi-inverse to that. So I'm using this dagger to mean like the R dagger is the quasi-inverse to the comparison functor. And now is where it's really, really useful that we're concrete over sets, basically. Because what's a coalgebra? Where a coalgebra is an object together with a morphism from the object into the comonad applied to that object, and it has to satisfy some axioms that I want to talk about. So now, since the co-limits in graphs are computed as in sets, so we can actually give a fairly simple description in terms of points of what the result of this comonad is. And the points of this of the resulting graph, right, the vertices of the resulting graph, can be described as a tuple where the first component is a saturated chain, and the second component is some vertex of the shape of the last shape. And it, well, if S could be equal to the source of the shape graph, then you would be counting some elements twice. So that's why you put this, like S has to be different from the source of that shape of that graph. But basically, it's a very concrete thing. That's good. Like this assumption of the right multi-adjoint really lets us express. We don't even need to use equivalence classes. We just put the saturated morphisms for this co-limit. And then, in particular, the coalgebra, we can look at how it acts on every vertex, right? It's a graph homomorphism, so it acts on vertices, and it sends each vertex A to some tuple, in particular, some saturated chain. So this is how we can obtain a tree out of the coalgebra. What we do is look at all the saturated chains that are in the image of this coalgebra map. And this, of course, ordered by prefix order and labeled with the obvious label as we've been doing, which is the domain of the last morphism. And well, this does turn out to give a functor. This functor does turn out to be a quasi-inverse. That's where the real stuff is, but I'm not going to talk about that. So the last remark, or like the last thing I'd like to try to explain, that maybe I should have tried to explain before, because this saturation thing really might really be surprising somehow. Like, why do we care? Like, if we could do things with a discrete category of shapes, why do we get into all this all these complications? And the reason is that not only it's interesting categorically, it's also interesting from the application side. So it is true that if we restrict to discrete categories of shapes, we can already do interesting things, and there is future work to be done just in that particular case. So for instance, we could do modal logic with a backwards modality. So in this case, our category of shapes would be discrete on these two bipointed graphs, where the only difference is which one's the source and which one's the target. And this would give backwards and forwards modalities, like traversal modalities to express properties of graphs. These are actually in the context of using graphs as databases or knowledge representation. These modalities are used, and we just get basically a comonad for this out of the formalism when no comonad was produced for this particular case before. I'm not saying it can't be done without it. I'm just saying it follows out from the framework very naturally. Now, there are things that we cannot do unless we add non-trivial morphisms, because these will allow us to give like more interesting semantics to these modalities. And of course, this will all be just intuitive, because I haven't given any syntax formally nor formal semantics. So all of this is just hand wavy, sadly. But the intuition that I want you to have, if this makes any sense to you, like maybe you have never seen a logical formula, modal logic or something, and it doesn't make sense, but the idea would be that when you put a diamond modality indexed by a shape S in front of a formula, what you're saying is that there exists a saturated morphism, not just any morphism, but a saturated morphism from that shape, such that the formula phi holds starting from the endpoint of that map. And I'd like to try to give an example again with this example category of shapes, with the diamond shape, the diamond graph, and the collapsed diamond graph, and the same situation where we have that the unique map from the diamond graph to the triangle actually factors through this morphism, which is incorporated, is part of the category S. So when we ask, well, does this formula holds in the directed triangle? This formula, we should read it as there exists a saturated morphism from D to our graph, such that true. So that's all. There exists a saturated morphism. And as I just said before, there is no saturated morphism. So this formula is false. It's false in the triangle, starting from the leftmost vertex. And so what are we saying? What is this modality expressing? Well, it is expressing the existence of an embedded diamond shape. We're not just asking that there is two successors with a common successor. Let's say that would be a way of expressing the diamond shape. We're actually saying that there's at least two distinct successors with a common successor. So this might, from the logical perspective, this sounds a lot like graded modalities in first order logic, for instance, where you say you can quantify, you can say there exist at least two elements X such that such and such holds. So this is definitely something that cannot be achieved if we don't include the maps into the category S. And this is very exciting.
Well, this for me is illuminating. So it tells me, again, a feeling for a saturated, this is a way of saying requiring conditions such as distinctness.
Yes. So in this case, it's requiring a condition of distinctness. There's this whole thing about whether we can actually include morphisms that look more like inclusions more than quotients in this category. But if this morphism was actually some kind of injection, then the condition would be more like there exists some shape that cannot be extended to some other shape.
Okay.
So logically speaking, it gets really interesting.
Yeah. Okay.
But yeah. In this case, it's definitely like a distinctness condition. Like you are requiring the existence of a certain shape where the witnesses for the different vertices are cannot be the same, because then they would be collapsed. They would then factor through some collapsed version of the same shape. So that's it. I was expecting to not take so long. So that's why I said I thought I was going bad on time. There is a slide about future work, but I just don't. I'm not sure it makes sense to read it completely because there's a lot of things to do. I'm actually excited.
Well,
about
just showing that there's a lot of things is important reason for doing the slide up.
Yeah, so the first one, maybe I already said it. I express a comonadicity result just for graphs, but it's obvious it works in more generality. So we are working right now on finding that right level of generality. And then there's different kinds of things. Like there's a conjecture about some property that I think holds in all cases. Then we have variants. We have various generalizations that should work to capture more logics. But maybe more importantly, we have to pin down the formal details of this correspondence with syntax and then give examples, because this should provide a lot of potentially interesting examples of logics that are captured in a parametric way.
The one question I'll ask is, we had these, like I said, there are a lot of things to do. Do you see if any of these is, higher priority than the others, or they're just all things that should eventually be done?
Definitely. So to formalize a relationship with this kind of generalized modal syntax is definitely a priority, because there's a lot. So we have to make sure we know the extent of applications we have just with what we have now, before relativizing and generalizing because all those things would imply changing the definition of S trees basically to something else. But just with what we already have, the things that I already explained to you, we have to see what are the logics that we can express in this way, and also I have a proof of this, but it was written late at night and I haven't reread it. So this would be interesting, right? Like this by similar companion property, it says that given any comonad D, like I showed you before, like this tree functor followed by realization, it's always the case that the conjecture is that it's always the case that if I start with any object, then the comonad applied to that object gives us back something that is bisimilar, and this would correspond to logical equivalence in the syntax side. And this is actually a property that is very useful from the perspective of finite model theory or research sensitive model theory, because it's even a big part of why people think that modal logic and variants of modal logic have good complexity bounds in terms of like the satisfiability problem. Well, this property is telling you that if you want to know if a formula is satisfiable, you don't need to look at all possible models. You just need to look at those which are of a certain form, which is those that are d of x for some x. And that simplifies that's a reduction in terms of like a computational reduction if you're actually doing algorithms on these things. So that's an interesting thing for sure. One of the first things is to make sure, like, to really clarify whether that's true or whether
coincidentally that actually ties into last week's talk.
Oh yes, I'm really sorry that I missed it, but yes, was it recorded? Because well,
it was on a similar it was on a similar theme of limiting the model, the examples you needed to check computationally and read.
Right. Okay, so yeah, I ended up explaining a little bit this slide, so great. So now definitely that's all I have. Yeah, so thank you very much.
Okay, thank you very much. Are there any questions from any participants? Hold on. Okay, seeing no questions. Anyways, ladies and gentlemen, thank you very much, and it'll be up in about an hour or so. Everyone else, next week is Christopus. How do you say his name? Christops, and hope to see you all there. Okay, we got some. Yanis said it's a nice talk. Anyways, this is a very nice talk, very clear. Thank you. Okay, ladies and gentlemen, take care.
Thank you.